the title of my talk is MEMS-based blood plasma viscosity sensor without electrical connections. I'm Onur Cakmak, and this project is being held at Koç University, Istanbul, Turkey. So I will make a brief introduction and about the blood plasma and about the concept of our system and show you the principle of operation, and then talk about microfabrication of our MEMS dies, MEMS devices, and describe the experimental procedure that we have conducted and show you the results, and then conclude my talk. So the main objective or so-called long-term goal of this project is point-of-care tests with whole blood. So there will be an independent reader unit and cartridge, so there will be no electrical connection necessity between the cartridge and the reader unit, and so it will help the cartridges to be disposable easily, and it will require low sample volume with a drop of whole blood. You will be able to make some analysis. So what are those analyses that we are planning to make? Based on viscosity sensing, mostly clot time measurements we are planning to make. But what about blood plasma viscosity tests that I will show you today? They are a step towards whole blood point-of-care tests with whole blood. So, on the other hand, also they are useful. This blood plasma viscosity is a useful parameter for the diagnosis of several diseases, just like cardiovascular or autoimmune diseases or myeloma. So, for healthy individuals, the viscosity level of blood plasma is between 1.1 and 1.3 cp. In the case of these kind of diseases, this blood plasma viscosity level jumps up to 1.8 and 3 cp range. So our system is based on a resonant microcantilever. So as I said, there are no electrical connections between the reader and the cartridge, and we have achieved a sensitivity of 0.01 cp viscosity, and now we can use the system with low sample volumes, and it can be further improved with improved designs. So what's the principle of operation? So our cantilevers are operating inside viscous liquid media, and when the properties of this viscous liquid media, just like viscosity and density, changes, this will have an effect on the dynamic behavior of this cantilever. So these are so-called hydrodynamic forces will be affected on the cantilever, and we are tracking the frequency, and then we are detecting the viscosity change by tracking the frequency with a specific method. So this is the illustration of our setup. As you can see here, there's an external coil, and this external coil actuates our nickel cantilevers, which are magnetic, and these nickel cantilevers are inside a liquid chamber or microfluidic channel, which is made of PMMA, and the readout is done by optical readout schemes. So in this project, in this work, in this presentation, all the results are taken with laser Doppler vibrometer. However, LDV can be replaced with optical interferometric readout schemes, which we have published before. So what's happening in here? We are exciting the system at a certain frequency, which is close to the resonance frequency of the cantilever. And then we are measuring the phase difference between this input signal and this output signal by using a lock-in amplifier. So when the frequency of this resonance behavior of the cantilever changes, we detect it by monitoring the phase. So as I said, there are no direct electrical connections to this MEMS die or cartridge. So that will create a benefit. So this is our microfabrication scheme. We have silicon wafers, and we sputter chromium and gold on top of it. The gold will be a seed layer for nickel electroplating, and then we use photolithography to obtain this geometry, the patterns, and then we electroplate this nickel, as I said, and we strip the resist, and after successive wet etching processes, we release our cantilevers. So they have 200 micrometers length, 20 micrometers width, and 2 micrometers thickness. So as you can see here, it's a very simple and one-mask microfabrication process. And this is the measurement setup. So you can see the MEMS die here. So there are microcantilevers on top of this MEMS die, and this is the LDV objective. And when we remove the cover, you can see this PMMA channel that I'm telling about. And there's a glass slide with which we epoxy bond on top of this PMMA microchannel in order to make sealing. And this is the inlet and outlet of the channel. So the cantilever, the MEMS die is here. And electrocoil is underneath the MEMS die. And you can see the heating wires. So temperature is very important parameter when you are making viscosity measurements. So we have a temperature controller unit. So these aluminum blocks also make the ability of making this temperature controller unit with 0.1 Kelvin precision. So this is a frequency sweep curve of the system in DI water. So our system has very low quality factors, as you can see here. It's around 5 or 6, but this is a general problem about the cantilevers operating inside liquid. So what we are making is, as I said, we are applying a constant frequency, which is close to this peak or so-called resonant frequency. And when the liquid inside is changed, when the viscosity is changing, this phase curve also shifts. And we are detecting the phase shift by using that lock-in amplifier. And this is a phase stability result for long-term observation of the system. As you can see here, we have a good noise floor, which is generally about, I think, quantization errors. So the standard deviation of the phase is 0.07 degrees around. So what we have done, the experimental process is like this. So we first characterize our system, our cantilevers, with certain glycerol solutions which have known viscosities. And the glycerol solutions we used are starting from 0%, which is DI water at 30 degrees, and goes up to 70%. So the viscosity range is varying between 0.8 cp and 14.1 cp. So after we obtain the response of the system to different viscosities, then we fill the system with blood plasma with unknown viscosity, and we try to predict the viscosity of blood plasma. So this is how the experiment goes on. So at first, as I said, we fill the system with DI water and then glycerol solution, and drain it again, and then fill it with DI water. And you can see here we have done it for several glycerol solutions. And what we make, we record the phase change between DI water and each glycerol solution. And you can see here 14% and 15% glycerol solutions, and we can distinguish these glycerol solutions between each other, and it corresponds to 0.03 cp viscosity difference. So we have also built a semi-numerical model using COMSOL multiphysics. So what we have done, we have a numerical finite element model built in COMSOL, and we added the added mass term and damping term by using the analytical expressions that are seen in the literature. And these are frequency-dependent parameters. So we make frequency-dependent analysis, frequency domain analysis for each glycerol solution in COMSOL, and the phase difference for each solution is obtained. And this is the result of the numerical model, this curve. And these are our experimental results. So the trend is similar. They have a good coherence, but there are some discrepancies which can be generally related with the liquid exchanges during our experiments. So some glycerol solution can remain inside the fluidic chamber, and that can cause a liquid exchange error. Also, some imperfections of the structures due to microfabrication can cause this discrepancy. So this is the viscosity versus. So when we put the glycerol percentage viscosity values on to this axis, so this is the viscosity versus phase change of the system. So where we are interested in this application is between 1 cp and 3 cp, as I said, the blood plasma viscosity level. So we zoom into this area here, and we fit a curve to these data points. And this is the curve that we will use for the predictions of blood plasma viscosity. So according to this curve, and according to our noise floor or stability, long-term phase stability, we have a resolution better than 0.01. However, as I said, we can have some problems with repeatability, and so that causes these discrepancies from this fit function, and so the accuracy of the measurements are around 0.02 CP. So for the blood plasma, what we have done, we collected blood plasma from 3 healthy donors, and then we have conducted the measurements at 37 Celsius degrees, and this reference curve is used for predictions. So what we do here is just the opposite of characterization. So we know the system response. So we know the phase change obtained with these blood plasma samples, and then we report this viscosity by using this curve. So as you can see here, all the donors were healthy, and the viscosity levels are as expected in the range of healthy blood plasma region. So actually, we didn't have any opportunity to make some experiments with unhealthy blood plasma samples because we have some contamination risk in our laboratory. So maybe in the future we will try to check it also if we can find some unhealthy blood plasma. So, but we can say here in medicine, it's said that this 1.8 CP is the critical point. So after that, it's a clue that the people has some problems with his blood plasma, his or her blood plasma. So we can distinguish 1.8 CP from these healthy donors. So the system works in that sense. So to conclude, it's a general sensor platform actually for viscosity measurements, and blood plasma is an application for it. And so it has a very simple microfabrication, and there are no electrical connections, which allows to make disposable cartridges. And so it has better than 0.01 CP viscosity resolution. And also multiplexing is available due to remote nature, as I said, because you can put several cantilevers and you can make several microchannels, and you can measure them at the same time with a photodetector array, or using fiber cables, fibers, you can measure it. So thank you for listening, and this project is supported by TÜBİTAK, which is Scientific Association of Turkey. Thank you.